This is the part 2 of me trying to build the most advanced and complex steering wheel for sim racing to have ever existed in this entire world. In this part, I'm going to talk about the whole architecture and electronics of how everything will work. Because see, I've taken inspiration from the RedBull family of cars, and all of these buttons and rotaries, whatever you see here, even behind, everything has to work like the actual thing. So if you haven't watched the first part, watch it before. And let's get started. This is the complete prototype that I built to test my theories before applying it to the actual thing. After I explain you the architecture, we will see a demo of how this thing works. So let's hop into my PC and show you the architecture. Welcome to Classes with Malhar, where I don't know what you learn, but you definitely lose brain cells. So let me know in the comments down below how many brain cells you lost till the end of the video. And let's get started. See, I want to talk about these things specifically and also the block diagram, so it will be easier to understand. And at the end, as you can see, the firmware also. Not the actual firmware because I just vibe coded it, but I'll show you the demo, how things work till now. So first the PCB, okay? So the PCB will basically contain an Atmega 328P, an Atmega 32U4 and a VOCOR display, okay? So as you might think, all of these three are standalone USB devices. So what I will have is, in that PCB I will have an inbuilt hub. So in that inbuilt hub, these three things will be connected. See, this is the chip I'm using. This is the USB 2.0 hub. Everything will be connected to this. As you can see, it has everything, including this ESD protection also. So it will be a little overkill, I guess, but it is what it is. I will just have one cable connecting from my PC to the steering wheel, and I don't have to juggle between multiple cables. That's the idea behind this hub. And apparently this is a standard practice also in the commercially available steering wheels, for sim racing. Now, let's talk about this point here. Why two MCUs? I keep on talking about these two MCUs in my previous video as well, and I didn't really tell you why we need two MCUs. So you will be very familiar with this chip, Atmega 328P. This is what is available on your Arduino Nanos, Unos, pre-common dev boards, right? And this Atmega 32U4 is what available on your Arduino Leonardos. The main difference between these two chips are, this Atmega 32U4 is an HID compliant chip, okay? That means we can very easily create our input devices with this, because whatever we press, suppose you attach a button in one of the pins of this Atmega 32U4, you can very easily detect it as a key press in your computer, like a keyboard of that sorts, right? In other hand, this Atmega 328P or your Arduino Nano, it is a serial device, okay? So I pulled up the pin diagrams of both of these Arduinos. Not that it matters, because we are gonna have these bare chips in our PCB, but this is a good representation of what to expect from the pins basically, right? So what we are gonna do is, on the Nano side, we are going to use this for basic telemetry, okay? So if you are confused right now, you might know about SimHub, right? So SimHub is a software that helps you to interact with your hardware, with your game. Suppose I'm playing a simulator game, SimHub will get all the telemetry data from my game and pass it to my Arduino. So that is what I am gonna use this for, is basic telemetry. Okay, I did telemetry. Come on, man. Basic telemetry, okay? That includes controlling the shift lights or RPM lights. These LEDs here, these are the shift lights, okay? And in specifically in our RedBull family of cars, you see there are these extra LEDs here, okay? These are specifically red LEDs, what I figured from a lot of footages, but as I have the addressable LEDs in my PCB, might as well I'll use them for these as well, right? So I will have a total of 25 WS2812Bs in my PCB. So that's one reason why we're gonna use it. The second reason is for switch logic routing. I'll come into this point in a bit. And the third reason is dual clutch logic, okay? So you might be thinking, what are these 2 points? I will come to them in a bit, but these are the 3 things specifically for which I am using this extra chip, okay? So by this you can understand that we are basically using this Atmega 3328P for telemetry and inputs pre-processing, you can say, okay? I'll write it down so that I don't forget. And this side of things is solely because of the game controller aspect of it. Basic HID device. So now, as you can understand, this right side is fairly simple. All the magic seems to be happening in the left side, isn't it? So now I will break it down. What I mean by switch logic routing and dual clutch logic, okay? I have separate points for this. See, all inputs and the routing. This is basically this, right? Switch logic routing. And by the way, this inputs routing and MPS logic is pretty much the same. So I'll cover them together. MPS means multi-position switch. So see, our steering wheel has these rotary multi-position rotary switches. See, this is a rotary switch, this is a rotary switch. Basically these all are rotary switches in the real car, but what I'm gonna do is I will use these 4 as rotary switches, but this one in the middle I will use it as a rotary encoder, okay? So that means all of these switches will be my rotary switch, and this one right here will be my rotary encoder, and this will have 3 states, so to speak. One is clockwise, other one is counterclockwise, and the third one is the switch. So in short, 3 states. If you have ever watched Formula 1, you might have seen calls like this.
Or shifts. Display 3 position 7. Let me know. Display 3 position 7.
So they basically use combination of the switches they have, right? So reason behind this is because a Formula 1 car is very complex and they have to control the whole aspect of the car, different things with their steering wheel itself. So that's why whatever many buttons they put, it becomes short, right? So they have to use clever routing to use 2 buttons in different combinations to achieve what they want for a particular setting, let's say. This is the complexity that I like. If you watch this channel, you know that already. I like complex. I want to replicate that complexity here as well. So what I'm gonna do is I will use these 3, switches, these 3 rotary switches, 12 position rotary switches, standalone. But one of these rotary switches, I will make it complex as By that, I mean I will make it so that I can use it with this rotary encoder. Let me show you what I mean. See, as I told you, I have these 4 rotary switches. I will use this rotary one along with this rotary encoder to have a multi-position combination switch. So I have 12 positions of this one rotary switch, let's say, which is this guy here. You see, I will use every state of that rotary switch using my rotary encoder as well. So my rotary encoder has 3 states, right? That is my clockwise, counterclockwise, and the switch, right? So for every state of this, I will have 3 states. That means one of those positions of my rotary switch will give me 3 different input options, right? So you can imagine now, using my 12 position rotary switch and this encoder here, I can have 36 inputs. For a good visualization, if I just duplicate this, all of a sudden I have 36 inputs from just one rotary switch. Isn't it awesome? Give this video a thumbs up for that. So now you might have a question in your head. How are we gonna route these 36 inputs to this HID compliant chip? So see, this is what I thought about, and this took me quite a bit of time to actually decide, is how are we going to extend the inputs. There are several ways. The most promising and standardized way I found it to be using shift registers. See, our steering wheel has a lot of buttons. Even if we exclude these 5 rotary thingies, because these will be connected to the nano anyway. I'll also talk about how I'll plan on connecting these buttons to the nano, but a little later in the video, and that doesn't really matter that much as well. But the point is, like, even if we exclude these 5 rotary thingies, we still have 1, 2, 3, 4, 5, 6,
7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18.
Around 18 more buttons. Those doesn't really need any pre-processing, so we can just straight up connect them to this HID compliant Atmega 32U4. But still, as you can see, there are not a lot of pins to connect 18 buttons in it, right? So we are going to need input shift registers, and as we have these 36 inputs as well coming from the nano side, so you also need output shift registers. So the paths will be like this. This will be our nano, or in other words Atmega 328P. I'm not writing the full name here. Then it will go to our output shift registers. Then it is gonna go to the input shift registers, and then finally to the Leonardo. So first, our buttons and rotaries, everything is connected to nano. I will in our firmware, which will live in the nano or the Atmega 328P, that will do all the routing and stuff, and then it will travel through the output shift registers to the input shift registers, and finally to the Leonardo or the Atmega 32U4, and like that it will be recognized to our game. This will be more clear once I go to the 6th, the block diagram portion. There I will explain this in even more detail. If you are this far into the video, consider liking, sharing with your friends and subscribing so that you don't miss out on the next videos. Okay, only 2 more things I want to tell you about these rotary switches before I go to this clutch logic. As I told you, I will only use this ROT1 for my pre-processing and such, and rest of these 3 rotary switches will be standalone 12 position rotary switches, so it doesn't really matter if I connect them to here or here, right? But I still want to connect them to this. Let me show you why. Okay, see, these are 12 position switches, right? That means something like this. This is the common, and there will be a wiper which will connect this common with these positions, right? This common can be connected to 1, to 2, to 3, to 4. So you can imagine, if we want to use this as a normal switch, we will need a bunch of pins in our MCUs, right? And well, I can use input shift registers, as I showed you before, to expand its inputs. But we also have to think about the PCB space, right? I'll show you the PCB at the end of the video. But long story short, we don't have that much of a PCB space, okay? So we also have to think about the connectors we are gonna use, the pins we are gonna have in the PCB for the connectors of these rotary switches, as we have 4 of these sort of rotary switches. So what I did is I did a resistor ladder approach. See, something like this. So you can pause the video and like see what's happening here, but basically there is a register ladder and we only have to deal with this one pin. You see this common? This will be connected to an analog pin of our MCU. In our case it will be a nano, and we can easily read the analog voltage levels. That will be, in this case, 10-bit value, that will be 0 to 1023, and we can just read the position of the rotary switch by seeing the value here. You divide 1023 by 12, or in this case it's 13 because I've used this 2.7k register even from this position 1 to ground as well, because this is a make before break sort of rotary switch, and while going from position 12 to position 1 it intermittently shorts the 5 volt to ground, so that resets the circuit. Don't ask me how I found out. That's the reason behind I added these extra 2.7 kilo ohm resistor. And right now I've tested this also. I'll show you the PCB. This have its own PCB, by the way, and it works really good with this. And also we save a bunch of pins with this. We only need one analog pin of our MCU. So we have 4 rotary switches. We will just need 4 pins. That's why I am using this with the nano, because theoretically we also need input pre-processing, because we need to read this analog voltage value, then determine the position of the rotary switch from position 1 to 12, and then route that through our shift register bus. I'm calling this, by the way, a shift register bus. Let me know if you can think of any better names in the comment section down below. Anyway, that's the reason even for these rotary switches, which doesn't really need that much of input processing, well, input pre-processing in terms of this sort of combination, but they do need the analog to digital conversion, as I'm using single pin for each of these. So I'll route them through the nano to basically have the same flow as I showed you for the first rotary switch. So that's it for the rotary switches then. Now we can proceed to the clutch. See, I underestimated the amount of things I did for this project. I'm working on this for the past 1 year. So this clutch logic and whatever is remaining, including the block diagram, I will show you in the next video, because this is already too long. For now, I will show you the demo of whatever I told you regarding that input preprocessor and this rotary switch routing. See, I also have this LED string attached. This is basically my work testing the telemetry data coming out from the game through this semaphore which lives in this nano and control this LED string with my car RPM and such. And see, this here is the rotary encoder. As I just showed you, these have 3 states, right? Which are clockwise, counterclockwise, and this button. And this here is a 12 position rotary switch. And this is my shift register network. This is an output shift register, which is going to the input shift register here. And that eventually goes to this Pro Micro here, which is a mini Leonard or whatever you want to call it. This basically is the HID chip that I showed you, right? This is the Nano, which is only responsible for the telemetry and inputs pre-processing. And this is my HID chip, which is responsible for basic game controller functions. And this is the standalone button here, which is directly connected to this input shift register. So this will represent all the 18 buttons that I showed you I have in my steering wheel. This is a 8-bit input shift register. So as this 8-bit output shift register, right? So I can have 8 inputs, one of which is consumed by this one right here, and the remaining 7 I will route them through my combination of this rotary switch and rotary encoder that I showed you. So let's hop into my computer and show you a demo of this thing, how it works. If you this far into the video, like, share and subscribe. See, I've connected both of these MCUs to my PC, right? And this is my string of WS2812Bs. There should be 25 of these, which is configured through my sim hub here. So there are some effects I've configured like anti-stall, ignition on, engine kill, car stall, and the RPMs. So these are the only things that I configured. I mean, obviously, this is just a test. You can configure everything else what you need. So let me show you that first. For that, I need to launch my game. See, I will start the car now. And can you see this LED blinking here? So see, for the telemetry LEDs, you might be able to see this blinking. See? So this LED will start blinking when we have ignition. As soon as we have ignition, it will start blinking here. Okay, and as soon as I start the car, you will see whatever I have LEDs in my dash, my LED string will also replicate it. 3, 2, 1. See? Now see, as I press the accelerator pedal, let me move off the line from this pit lane to show you more of the telemetry that's getting reflected in this LED string here. See, this is the anti-stall indicator. See, the ship lights working as they should. Now let me show you the rotary routing in the firmware. See, this rotary switch here is this rotary 1 here, and as I change its position, my firmware can read the actual step it is in. As I showed you, I am using only one pin, as you can see. See, 3 wires are coming out of it. One is the VCC, one is ground, and another one is the analog pin, which is connected to one of the analog pins of my Nano here. And my firmware can easily detect the position. So this works really good. And as I'm using this with this rotary encoder here, you will see I'm routing these positions through my shift register network here. So let me open another software called MMJoy, where I'm building the firmware for my HID chip here. And see, this button here, as I showed you, this is a standalone button connected to the HID chip here. If I hit it, see, this one is lighting up, isn't it? And currently my rotary position is 1, so you will see the clockwise lights up the 4 and counterclockwise lights up 2. See? And this switch here lights up 3. Works really good. And now I will put this rotary switch to position 2, and you will see this routing will change now. See, now it's 7, 6 and 8. Isn't it incredible? I can show you only 2 because, well, it is an 8-bit shift register, so it can only support 8 inputs. But you already got the idea, isn't it? Now we can use these HID inputs to our game and control specific things with it. Let me show you what I mean. See, I have my rotary to 1. That means my things will be routed to 2, 4 and 3. Now these 3 buttons I can use in my game. See, I've mapped it to brake balance offset adjustments. And see, it works flawlessly, isn't it? Isn't it awesome? Give this video a thumbs up if you liked it. Also subscribe and hit the bell icon so that you don't miss out on the next videos. In the next video, I will show you the dual clutch logic and routing. I will show you why we need this 2 clutch pedals. What's their significance? Till then, goodbye and peace out. I'll see you in the next one.